Go. Okay. Right. We went over the quiz. We went over the survey. Let's review. Last time, what did we do? So a couple of things. If gamma 1 and gamma 2 are homotopic, there's a deformation from one to the other that's continuous, and they start and end at the same points, then the integral over f1 is the integral over f2 of a holomorphic function, f. We discussed simply connectedness. So if omega is simply connected, that is any two curves starting and ending at the same points are homotopic. Then all kinds of things, including the integral over a closed curve of any holomorphic function, is 0 by the same argument. And we used that to prove that, in particular, if you integrate over we use that to prove a topological statement, which is that C take away 0 is not simply connected. And the proof is that the integral of 1 over z, dz, over the unit circle is not 0. And then we defined a logarithm function. So if omega is simply connected and it contains 1 and it does not contain 0, then we can define a logarithm function for omega by integrating any path that goes from 1 to z of 1 over w dw. This is holomorphic, and it has all kinds of logarithm-like properties on R. In other words, in a ball in some disk of radius epsilon around 1, wherever that, since 1 is in omega, this log omega really is the usual real log. That's one thing. And another thing is that if you take e to the log omega of z, you get z back. So it's the inverse to the exponential function. We talked about the principal branch of logarithm, right? That's where we stopped. We did the principal branch. The so-called principal branch of log is when you take omega to be the slit plane. So if you take the complex plane, you remove 0 and infinity, and the argument ranges from minus pi to pi. That's the principal branch. And for the principal branch, if z equals r e to the I theta, and theta is ranges from minus pi to pi, then log for the principal branch of z is what it should be, the real log plus I theta. Okay, it's a nice holomorphic function, but again, log of zw is not in general equal to log of z plus log of w. All right. I think that's where we stopped last time. Is that about right? Okay. So remember this proof, the proof of this statement. I just want to discuss this for a second. The proof, we narrowed it down to being able to prove things about two nearby curves. There was like a gamma S1 and gamma S2, and S1 was close to S2. And I gave two proofs. One proof was that if we break these up into little regions, little intervals, then the intervals differ by a constant, and that constant keeps changing to the difference between the endpoints of the two primitives, and until we get to the very end, and the endpoints agree. And the other argument, I mean, we sort of talked about this briefly, but I wanted to discuss it in a little bit more detail. The other argument, so proof one is that if fj is the primitive on disk j, then the integral from, we have these points z1, we have these points z1, w1, z2, w2, out to zn, wn. Okay, so the integral from z1 up to z2 of, or zj up to zj plus 1, whatever, of that primitive, of that function, of the function f that we're trying to evaluate, is the jth primitive, the jth primitive at zj plus 1 minus the jth primitive at zj, and they differed by you remember this, right? The two, each primitive on the intersection differs from the previous, so this is on dj intersect dj plus 1, or minus 1, okay, plus 1. On the regions where they intersect, we have two primitives. They have the same derivative, so the difference in the derivatives is 0, so they differ by a constant. And we have different constants as you transition from one to the other. I mean, right, this is like the primordial idea of sheaves. These constants keep the difference between the sum along the top curve and the sum along the bottom curve. Should I give the whole proof again? I think you see what I'm doing. The difference between this and this only came out to fj of zj plus 1 minus fj of wj plus 1. It was just the difference at the endpoints. And you iterate this until the endpoints meet again. Okay? Iterate until endpoints meet. All right. That was kind of the first proof, and that was conceptually not such a hard proof. Proof 2, which was really proof 1, was, okay, you have these overlaps, and you have on the overlaps, dj intersect dj plus 1, you have two primitives. So just adjust one of them so that, remember, they differ by a constant. Adjust it so that the constant's always 0. So that really makes it feel like there's a global primitive. So there is, by analytic continuation, a global primitive on the union of all of the disks. Okay, and there really is, but only if you don't allow the first disk and the last disk to overlap. Okay, and there really is. What I'm trying to say is, I think this is actually how Riemann discovered the theory of Riemann surfaces. There really is this chain of primitives. It's just that when you start with disk 1 and you start doing this chain, the danger is that you'll come back to the original, that there will be an intersection of disk 1 and disk n. Here's disk 1 again. And so the idea is don't let these intersect. Well, how can you not let them intersect? So really, what's happening, for example, for the logarithm function, so there's another log, there's like the Riemann surface log Riemann surface. Because log is the main culprit in this. What's really happening is the slit plane, as you go from minus pi around to pi, well, you should be able to keep going. You should be able to extend this chart. There's nothing wrong locally with all of these different values of log. But as I extend the values of log across here, now I have to change, right? There's a log on each disk. Let's say it like this. On each of those disks, let's call them dj, there exists a log dj, which is integrate from, I mean, it's a log up to constants. So in other words, there really is a log here, but then there are other antiderivatives of 1 over w as you go around all of these disks. So what's really happening, the way Riemann realized that one could think about this, is that the disks here, so this is with argument, if you grade this by argument, so I'm going to make the vertical line argument. We start at argument negative pi, right? You know what I mean by argument. R e to the I theta, theta is the argument. So we start out here with a disk near negative pi. And as we move the disks around, the argument rises. And as we get all the way to pi, and this is at each, so it's sort of at each height of argument, I have another complex plane. I have a complex plane here. I have a complex plane here at height 0 when the argument is 0. That's this plane. When the argument's negative pi, that's this plane. And when I come back around to the argument being pi, now I'm here at height pi. And that's this plane. And there's nothing wrong with this disk. It's just that we're looking down from above at these disks, and it looks to us like this disk has overlapped this disk, because this disk is overlapping this disk. Let's color these. So we have this disk, which is up here, which is overlapping this disk, but it's really down here. So the way to really think about log holistically is as an infinite spiral. So really, you can think about log C, or some infinite extension of C, as being a function that takes values in C cross R. So at every value of the argument, there's another plane. And as you follow one plane around, what it does is it spins around. So you're never allowed to take C minus 0. You're never allowed to take C of 0. Log of 0. You're never allowed to take log of 0. But you sort of, if I were to show you one kind of branch of this, it's something that looks like this. It's this infinite spiraling staircase, all the way up and all the way down forever. And on this function, so on this, it's not a function, right? It's a multi-valued. It doesn't take a complex number and give you a complex number. It gives you all the possible values of that complex number, because what you're really seeing is the projection as you look down. As you look down from above, you're seeing all possible values that are separated by 2 pi I, right? So this gives sort of all possible values if we look from above. If we look from above, and the act of taking a branch cut is to say, okay, these are the values we want. and act of taking a branch cut specifies exactly which value log should take. So no plus or minus 2 pi I ambiguities. I mean, times an integer ambiguity. Does that make sense? So there really is a global antiderivative. Just when global, you have to expand your mind about what global means. All right. So in a similar way, so here's another similar theorem. Let a region omega be simply connected. Let me say something else first. So here's another point. The point of what I'm saying is, let C be any, I guess I can call it gamma, be any infinite simple curve that goes from 0 out to infinity. Okay, so you take 0, you remove 0, and then you go out to infinity however you want. It's simple, it doesn't cross itself. Simple, doesn't cross itself. In other words, it's injective. And goes to infinity means for all, goes to infinity is that for all r, gamma, so let's parameterize gamma as going from 0 out to infinity to C. For all r, the set of times t, so that gamma of t has absolute value less than r, is bounded. Okay? In other words, I take some disk of radius r, let's say a big disk. So there are times when I'm inside the disk. The collection of times for any r, the collection of times when I'm inside that disk for any fixed r is a bounded collection of times. So in other words, I escape any disk. So any simple curve that escapes any bounded region, then there exists a function log on C minus the curve. C minus the curve is simply connected. So the exterior of this cut is connected and defines, you've basically taken a cut of this infinite spinny thing. You've taken a cut and said, these are the values I want log to take. There exists a log on this such that the usual things, exp of this log is equal to z, is the identity. I'm not doing anything new. I'm just saying, well, the curve could even go through 1. The only reason we said 1 was so we could compare it to the usual real log. There's no, that doesn't make any difference. There is a branch cut. You pick any so the proof is pick any z0 in the region, this is omega, and let log omega, as usual, be the integral from z0 to z of dw over w. Okay, so I just want to say something a little bit more general, which is that this curve is what's called a branch cut. So gamma is called a branch cut. And of course, the principal branch cut is the one that just starts at 0 and goes right out to minus infinity. That's what that standard curve is. But there's nothing special about that curve. What's really going on is that there's an infinite spiral, and you just have to tell me which piece of the spiral you want. And they'll all be the same up to a constant, and you don't have to tell me where to cut it. Don't cut it straight along this 0 to minus infinity line. Cut it along any subcurve you want, as long as what it leaves behind is the entire complex plane minus a curve that misses 0 and goes out to infinity. Okay? Does that make sense? Let me say one more thing. I promised you a break, so let me say one more thing very quickly, and then we're going to move on to a new topic. Let me say one more thing very quickly, which is complex exponentiation. What is complex exponentiation? So we know what real exponentiation is, right? What do I mean by root 2 to the pi? What does that actually mean? Have you ever thought about what that actually means? You put it on your calculator, it gives you an answer. What does root 2 to the pi mean?
Well, there's like a unique, like real valued function that goes through like the integer ones and satisfies all the properties we want it to satisfy, like with approximating birationals and stuff.
Exactly, exactly. So we can approximate root 2 birationals, Pn over Qn, and we can approximate pi birationals. Pi is the limit of, let's say, Rn over Sn. And then you prove a theorem that Pn over Qn raised to the Rn over Sn. We know what it means to raise to integer powers, and we know what it means to take roots. This is an integer root. Of course, if this is a positive number, this number is bigger than 0, then there's no problem saying what all of these things are. And we show that this is a Cauchy sequence and it converges to something. And the thing that it converges to is root 2 to the pi. Okay, now what does I to the I mean? What is I to the I? Well, I to the I, very simple. I is right here. So I is e to the pi I over 2. Pi I over 2. E to the pi I over 2 is I. And so if I take that and I raise it to the ith power, I get e to the negative pi over 2. Cool. I to the I is e to the minus pi over 2. That's fun.
But I isn't just e to the pi.
But I isn't just e to the pi I over 2. I is also e to the 5 pi I over 2. And if I take that and I raise it to the I get e to the minus 5 pi over 2. And this is really a problem. These are two completely different real numbers. They have absolutely different magnitudes, okay? We're way off. We're not even close. So what's the problem? Which one's right?
You have to choose a branch for your log.
You have to, it depends on which branch you choose. You choose the branch, you decide what I to the I means. Okay? So what's really happening over C, z to the w means, by definition, z to the w is the exponential of w times log z, and you have to tell me which branch. You give the branch. It has no meaning. And I don't just mean it has no meaning up to, it has a meaning up to 2 pi. right? If I change this to a different branch and I shift this, if I shift log z by 2 pi I, in other words, I just choose a different point on the branch. That's really the only ambiguity, right? The value z to the w shifts by a factor of e to the w times 2 pi I, which depends on w. So now you're really in trouble. If you don't choose a branch cut, you're really in trouble. You can't just say up to multiples of 2 pi I. It completely changes the meaning of these things. Okay? So it's essential that you choose a branch cut before you speak of exponentiation. All right. And one last theorem. You don't just have to think about numbers, you can think about logs of functions. So this is log of a function. You can define log in terms of a function. So here's a theorem. If f on a simply connected, so simple connectedness is used every single argument here. The simple connectedness means I want to just take some base point and integrate out to z, 1 over w dw. In order for that not to matter which curve you took, we need the simple connectedness. So simply connected. But now we don't care about whether it includes the value 1 or 0. That's not the issue. And f is non-vanishing on omega. Then there exists a holomorphic function g, which we should write as log of f. What do I mean by that? So there exists a holomorphic function g such that if you take e to the g of z, which is a perfectly fine thing to do to a holomorphic function, it's just a composition of two holomorphic functions, you recover f. Okay, does that make sense? G is not unique. You shift g by 2 pi I, you get the same, so not unique. Proof. How will we define g? So we have our region omega. Let's fix a base point. Fix z0 in omega. Totally arbitrary. Let g of z be defined as, what do you think? How are we going to get something that will behave like log f? If we just want log z, we would do 1 over w dw.
Is it like the integral of the logarithmic derivative?
F prime over f.
Yeah.
F prime over f. Perfect. You integrate any curve from z0 to z, any curve. F prime over f. F in the denominator is not 0. So this is holomorphic. This is holomorphic. Omega is simply connected. So independent of the choice, independent of the path. And this is a perfectly well-defined function. So this is a nice holomorphic function. Nice holomorphic function. Holomorphicity is proved as usual. If you take g of z plus h minus g of z, that's zooming in on z changing by a little bit. So you can take a straight line or whatever, and this will be continuous in that area. And we've done this proof 10 times now, right? holomorphic, look at g of z plus h minus g of z. And this is the integral from z to z plus h, dot, dot, dot. I'm just reminding you how we prove these things. Does that make sense? Okay, so the sense in which this definition is supposed to be the log function is that e to the g needs to recover f. So, how can we prove that?
Take log.
Say it again.
We take the log of this domain.
The domain, when we made log on a domain, we needed to know that 1 was in the domain and 0 was not in the domain. Actually, it doesn't matter that 1 is in the domain. You can take any base point, but we need to know that 0 is not in the domain. So here, we've already made a log. So don't think of this isn't really a log. We just made a function g, and it has, what we're trying to prove is that it has this property e to the g is equal to f. So it's, I'm seeing how much we followed from last class. Let's do this. Let's look at f of z times e to the minus g of z. That's exactly the same thing we did to convince ourselves that log. So let's look at this function. Let's look at its derivative. Right? So what's the derivative? Chain rule. F prime times e to the minus g plus f times e to the minus g times g prime. And what is g prime? G is defined as an integral, fundamental theorem, f prime over f. And there's a minus sign from g prime, minus g. So the derivative is 0, and so the two functions agree.
So where does the non-uniqueness come in?
Oh, if I change g by 2 pi I, if I take this and I add 2 pi I to it, e to that function will still be f of g.
Right, but like, is there a way in which that, like, we seem to have chosen the logarithmic derivative very, quotes, uniquely. So does that correspond to, quotes, non-unique choices of of logarithmic derivatives, if that makes sense? Like, are there different logarithmic derivatives?
No, it's just that I could have taken this function and added 2 pi I to it. This choice is in some sense canonical, but I could have taken 2 pi I, I could have taken this choice and added 2 pi I to it and still had this equation be satisfied. So I agree, this is kind of the canonical choice that I would make, and it would determine the function uniquely. There's still something wrong. The derivative is 0, and therefore this is constant. What constant is it? So f times e to the minus g is constant. I'd like that constant to be 1 so that this equation is satisfied. But what constant is it? Well, as things stand, let's see, let's evaluate it at z0. That's the easiest place to evaluate. So evaluate this at z equals z0. I get f of z0 times e to the minus g of z0 0. So the constant's coming out to f of z0. So it's not quite right. We want it to come out to 1. That's easy. We just have to shift g. This is going to answer your question right now, Thomas. So need to shift g. Need to shift g by a constant. Well, f of z0 is non-zero. So there's a choice of log. So there exists a choice of log such that, in other words, there's a choice, let's call this W0, which is log of Z0, such that log of f of Z0, f of Z0 is the thing that's not 0, such that e to the W0 is equal to f of Z0. So G should really be, I guess I need to subtract this constant off. The integral from any curve going from Z0 to Z, f prime over f minus W0. Is that right? Minus W0 or plus W0? I think it's plus W0 because I want the value at Z0 to match W0. So I want plus W0. So if I make this choice of G, if this is G, then when I look at f times e to the minus g evaluated at Z0, I get f of Z0 times e to the minus g. G is an integral which evaluates to 0 plus this constant W0. And so I get a factor here of e to the minus W0, but e to the W0 is f of Z0, and I get f of Z0 times 1 over f of Z0. Now it's equal to 1. So now, Thomas, let me ask your question again. Let me ask your question back at you. Why is there a canonical G? There's a canonical this part.
There's no canonical W naught because we need a branch of log.
But there's no canonical W naught. They differ by 2 pi I. It's because we didn't finish the calculation that we didn't see the non-canonicalness, or whatever. Okay? So it's clear that the answer couldn't be unique because here you can see if I change G by shifting by 2 pi I, I still satisfy this equation. Why didn't we see it here? It's because this was the wrong function. We were missing the condition that this is equal, that constant is equal to 1. And the way to make that constant is equal to 1 is to shift it by something. Which something? You have a choice. Does that make sense? All right. Should we take a break or should we just go 10 more minutes? Votes for a break? Votes for keep going? Most of you didn't vote. I guess that's democracy in this country. Well, I saw 1 vote for keep going and 0 votes for take a break. Let me think for a second. Let's take a 3-minute break. We'll reconvene in 3 minutes. Okay, so we only have a few minutes. Let's do a little primer on Fourier analysis. Fourier series, not to be confused with Fourier integrals, which is where we're headed next. But here's a little theorem. Let f be holomorphic, let's say on a disk. Holomorphic. Then, and of course it's given by a power series, has a convergent power series. Then for every n bigger than 0 and for every r less than the big radius, if I take 1 over 2 pi times the integral from 0 to 2 pi f of z0, so z0 is the center point of my disk, z0 plus r e to the I theta. So if this is z0 and here's my disk of radius r, So I'm evaluating f on the boundary, and I take the Fourier transform of that, e to the minus 2 pi I n theta, but theta goes from 0 to 2 pi, so I don't need a 2 pi here. So just n theta, d theta, these ANs, these coefficients of these power series coefficients are also Fourier coefficients. So power series coefficients are also Fourier coefficients. About any circle. So I'm taking, this was big R, and then I'm taking a circle of radius little r. Any little r smaller than big R, I take a little circle and I integrate f around that little circle, twisted by e to the minus in theta. So this is like the Fourier transform on this circle. And what that recovers is, I claim, exactly the nth Fourier coefficient of the function. Okay, does that make sense? And here's a crazy thing. It's not so crazy. And if n is less than 0, then if I take this Fourier coefficient, e to the 2 pi I, f of z0 plus r e to the I theta, e to the minus I ni theta, d theta, exactly the same formula, but now n is negative. Instead of spinning in a positive direction, n is spinning in a negative direction. The integral vanishes.
So if we had a pole, would that still
That wasn't
be the case?
holomorphic.
Right, okay.
Yep. Yep, exactly. Exactly. Okay. You'll see immediately when we look at the proof. Okay, so again, I'm assuming f has a power series expansion in the disk of radius r about z0. So what is an? The nth Fourier coefficient is just the nth derivative at z0 divided by n factorial. Right? You differentiate n times, n comes down to n minus 1, n minus 2, and so on. You kill off the early terms, then you have z minus z0, and then lots of future terms. But when you evaluate at z0, the future terms are gone. And so all that's left is an. An times n factorial. I'm just reminding you the proof of this statement. Why is the nth power series coefficient equal to this? But now let's apply. So I have a 1 over n factorial, and I have a formula, the Cauchy integral formula, for the nth derivative. That's 1 over 2 pi I, integrate over a circle of your favorite radius r, about z0, and f of w over w minus z, now to a power which isn't just 1, but n plus 1, that's what will get us the nth derivative, dw. And there's a factor of n factorial. You remember this formula? Okay, the n factorials cancel. How should we parametrize w on this circle of radius r around z0? How about z0 plus r e to the I theta, as theta goes from 0 to pi, 2 pi. Right? If I make this parametrization for w, for our dummy variable w, then that'll start at z0, but then it'll shift by r and go around a circle. Okay, so now I have 1 over 2 pi I, and integral theta goes from 0 to 2 pi, 0 to 2 pi. F of w is z0 plus r e to the I theta. Divided by w minus z to the n plus 1 power. W minus z minus z0 is r e to the I theta, to the n plus 1 power. But then I need w prime, right? W prime d theta. W prime, this is a constant, and I get r e to the I theta times I, the chain rule, d theta. And the I cancels that I, r e to the I theta cancels one of these. And let's look at our formula. And notice that I missed a factor of r to the n in the denominator. Because now we have exactly what we wanted. There's a 1 over 2 pi. There's an r to the n. There's f of z0 plus r e to the I theta, and e to the minus I n theta, d theta. Thomas, you were going to ask something?
I guess it's like another question, but like, do all periodic functions whose Fourier coefficients are like behave like this, like there's 0 for the negatives, do all of them emerge from some holomorphic function?
Yes, because if they're 0 on the negatives, then they have a power series. A convergent, as long as they have a convergent power series, as long as these ANs have a positive radius of convergence in the Hadamard formula, and hence they're holomorphic, because power series are holomorphic. So this was if n is bigger than 0. Now if n is less than 0, then what do we get? If n is less than 0, let's look at the integral. 1 over 2 pi, I have an r to the n, integral from 0 to 2 pi, f of z0 plus r e to the I theta, e to the minus I n theta d theta, right? It's the same exact formula. But reversing the previous argument, this is exactly 1 over 2 pi I times an integral over a circle of radius r about z0, f of w, w minus z to the minus n minus 1, dw. Exactly how we got from here to here, it's the same thing. I guess there's no 1 over r to the n. Let's see for a second. R to the n, e to the minus n theta. No, that's right. And there's a 1 over 2 pi I. The i's cancel here and here. And this integral is exactly this integral. I'm not missing any factors. But n is less than 0. N is less than 0, so negative n is bigger than 0. N's an integer. So negative n minus 1, this power is bigger than 0. So the integrand is holomorphic. So the integral is 0. Okay, so we're seeing that the Laurent series expansion of f has all the negative coefficients equal to 0. But we're seeing that by averaging f, what are we doing? We're averaging f. I mean, let's get an immediate corollary, the mean value theorem. Mean value property principle is that if you integrate over a circle of any radius, 1 over 2 pi I, f of w, dw, you get back f of z0. You take any circle of any radius, you integrate f, you take the average value. Sorry, do I have an extra I that I don't want? Yeah, this is right, but it's not how I want to say it. Let's say it in a parametrized form. If I take the value of f at z0 plus r e to the I theta d theta. Okay, so I take all of these values around the circle and I average them, I get exactly the value of f at z0. And that's just the previous formula evaluated at n equals 0. All right, let me give you just one more corollary. This is a fun kind of, we get this for free. If u is a function, a real valued function, u is twice, not infinitely, twice continuously differentiable, so that I can define a Laplacian. And if u is harmonic, so this is harmonic, I remind you that the Laplacian is 2 derivatives in x plus 2 derivatives in y. Anytime you have a harmonic function on a disk, then if you integrate 1 over 2 pi on a disk, so let's say 0 to 2 pi, u of z0 plus r e to the I theta, d theta, you get u of z0. How would I prove such a thing?
We had an exercise saying there's a unique holomorphic function with real part u, right?
There exists a holomorphic function with real part of f equal u. It's not unique because if you change it by
oh, right, yeah.
but it's yes, essentially unique. That's it. Okay, so a couple of little baby warm-ups in Fourier analysis, and we're going to get to much more serious Fourier analysis on the line, which is non-compact, has a completely different property. At least technically has rather different properties from the compact Fourier transform on the circle, the dual of which is the integers. The dual of the real line is the real line itself. So we'll get to all of this on Tuesday. Any questions?